Had a question about banked curves and how they relate to incline type problems we were doing before. And so here's two cases, case 1 and case 2. Case 2 is a banked curve. So I'll put in here, this is a banked curve. And case 1 is just an old-fashioned incline where the block is sitting there. And it's going to slide down the incline. Now what we did with those is we changed the axes. I'm going to call them P and Q just so it kind of alleviate confusion. And so we put everything into the P and Q. And so here you've got, we take mg and break it into its pieces. You can figure out that that's the angle theta. And so the mg going down the incline in our negative q direction is mg sine theta. And then over here, the one that's pushing into the incline is mg cosine theta. And so if we do the sum of the forces in the p direction, that comes out to be 0, because in this case acceleration in our p we know is 0, and acceleration in our q is not going to be 0 because it's going to slide down and accelerate down the incline. So the sum of the forces in p equals 0, and what you do is you get n minus mg cosine theta equals 0. And so you get this equation that you get kind of used to, mg cosine theta equals the normal force. Now, for a banked curve, this thing is moving around in a circle. So you've got this kind of weird picture. I draw it kind of like this here to kind of show what's happening. So you got these, and the car is kind of going around in a circle, through these banked curves. And so what's happening is you're going to have an acceleration pointing inward there. And so in this case, it's easier to keep things in the traditional x and y axes. And so that means you got to break the normal force into pieces that are in its x and y. And so when you do that, it'll turn out that this is our angle here, theta, and so that this side will be n sine theta, and then this side will be n cosine theta. And so we do this equation, f in the y direction. Now in our case here, the acceleration in the x is not equal to 0, but the acceleration in the y is equal to 0. So basically, with these kind of problems, what's really important is for you to figure out in what case, in what direction are the accelerations 0, and then that makes it easier to decide which case you want to do, the regular x and y or this kind of twirled p and q. And so because the acceleration in the x direction here is not 0, but the y is 0, it's more natural to keep the axis this way here. And so in the y direction, the forces would be n cosine theta minus mg equals 0, and you get this equation that seems very different. Okay, n cosine theta equals mg. And so a couple of things, I'll make a comment here. So over here, the normal force is exactly just enough to balance out the cosine component of mg. Over here, the normal force is kind of doing a couple different things. First of all, normal force is going to be what's balancing out the mg, as we see from here, but also the normal force is going to be what's responsible for this acceleration. So the normal force in the second case, by definition, has to be bigger. And so let's label this as n sub 1, this is n sub 2. And so if I solve for n sub 2, I get mg divided by cosine theta. Okay, and so that means since cosine theta is going to be less than 1, n2 is going to be bigger than mg. So we see here that n2 has to be bigger than n1. And again, conceptually, the way that I would say that is because the normal force is going to be pressing more, okay, in order to account for this acceleration. So if you were in this banked curve, you would feel heavier than you would in this case over here. And again, the key is to figure out which way your accelerations are working.